Hello, I'm Ed Morehouse. Welcome to the category theory portion of the summer school. So as I've been talking to some people in the break and at lunch, they said, you know, I hear category theory is great and all, but what's it good for? And well, luckily I don't have to answer that question too much, because at the summer school you have two other speakers, Patty and Noam, who will be telling you about some pretty fancy applications of category theory to real PL problems. But my talk is just introducing you to category theory, so I won't assume that you know any category theory, although many of you may, and that's fine. I'm going to start at the beginning and just go through some basic definitions and constructions. And my motivation is twofold. So first, sorry? Could I speak louder? Well, let's see if I can move this closer to my mouth. Okay. Yes, then I can speak louder. Is this better? Okay. I'm not going to start over, but I'll just pick up from where I was left off, and I'll say my motivation is twofold. First, I want to introduce you to some basic constructions that you will need to follow Patty and Noam's lectures later. And secondly, and probably more important, I want to introduce you to a style of reasoning, because in category theory, the kinds of arguments we make are quite different from the ones that we make, for example, than the ones that Dan and Bob presented to you earlier today, in that we can't access the things that we're talking about directly. We can only access them through their relationships with one another. And that's what I want to emphasize, and what I want to sort of show you how to start reasoning in that way. Okay, so before I get started on real stuff, let me just try to give you some motivation and intuition for what that's worth. And you can take this all with a grain of salt, because it's very subjective and high level, and you know, there are lots of ways to think about this, and I'm not saying that this is the only one or the best one, but for what it's worth, right? So one way to think of category theory is as a kind of generalized set theory. Oh, I should write bigger. Okay, well. Okay, and the idea here, okay, is that in set theory, our primitive notions are those of sets and this membership relation, right? Now, we want to sort of reimagine this from a different point of view. So instead, we think of our primitive notions as still sets, but now instead of the membership relation, we consider functions. Okay, that is the maps between sets. And now we're in a position to generalize yet again, in that we don't have to imagine that the things that we're talking about are sets at all. They can be any sort of thing, which we'll just call objects. And we don't assume that the maps between our objects are necessarily functions, but they're any kind of mappings between objects. And we'll just call those arrows. Oops. So I promise I'll do better with the board management in a second. So, okay, so what? Well, this allows us to, well, what do we assume about these things? Well, we just assume that they have a composition structure. And to explain that, probably the best way is for me to tell you about these great things called Legos. So Legos are these toys. They come in little discrete pieces, and you can assemble the little discrete pieces into anything you want, basically. You can make like the Death Star out of Legos. It's really neat. And but when to make something out of Legos, you have to put the Legos together. And you know, since I have only two hands, when I put Legos together, I generally like do this pairwise. And then when I'm done, when I've made the Death Star, the order in which I assembled the Legos into the Death Star is not recorded anywhere in the Death Star. All that's left is the Death Star. So the point is that the order of the composition, of putting things together, is irrelevant. but that only the configuration of the things with respect to each other matters. Okay? So this composition structure recurs in many, many kinds of systems that people want to study, from areas of pure math to aspects of programming language theory and many other places beside. And by making such few assumptions, we give ourselves what Bob has called axiomatic freedom, which means by making fewer assumptions, we can describe more things. So this sounds great, but if we take it to its logical extreme, if we make no assumptions at all, then we can describe everything. But unfortunately, we can't say anything at all about it, right? So we want some kind of happy medium where we make the assumptions that recur in a broad range of structures that we want to study, but not anymore. And I would argue, at least subjectively, category theory does a good job of hitting this sweet spot of axiomatic freedom. And we don't lose anything by this because we can always selectively reintroduce assumptions as we go, right? But then they're sort of domain-specific assumptions rather than global assumptions. Okay, so this perspective of reasoning in terms of objects and arrows forces us to reason what I call behaviorally. So maybe sticking with the theme here, I'll do this. Rather than reasoning structurally, as Bob and Dan explained to us how to do about some aspects of programming language theory this morning, we have to reason behaviorally. Okay, and that's basically the theme of all of category theory. And so let me try to make an analogy to explain this point a bit. So imagine that you're a biologist and you want to understand how frogs jump. So one thing you might do is go out into the marshes and catch a frog and then anesthetize it and pin it down to a table and then cut it open and look at its muscles and its nerves and try to maybe look at its tissue under a microscope and try to understand how the parts of a frog work together to make it jump. Okay, now if on the other hand, you're a sociologist and you're studying people and their behavior, then you have to use a different technique probably, right? So you're able to observe what the people do and how they relate to each other, but you can't, well, okay, nowadays maybe you can put them in an fMRI machine or something like that, right? And see something about what's going on in their heads. But at least, to a great degree, the way that you understand what's going on is to just observe what are they doing, how do they relate to each other. And that's the idea of category theory. You look at the objects, you don't assume that they're sets or anything else for that matter. You just look at how they relate to each other by way of the arrows that mediate between them. Okay, so that's my 5-minute high-level overview of why category theory. You can take that for whatever you think it's worth. Okay, so let's get down to brass tacks. This is category theory. The first thing I should tell you is what is a category. Oh, I promised I'd write bigger, so let me do that. Okay, so a category starts with the following data. First, we have a collection of objects. So let's give this category a name. I'll call it C. I'll use this convention to use Blackboard bold variables to represent variables that range over categories. So we have a collection of objects called C with a subscript 0. And you should think of this as the 0-dimensional part of C, like points, the discrete stuff. Okay? And then for notation, we write A:C to mean that A is an element of this collection, C0. A is in the object collection. Next, we have an arrow collection. C sub 1. Okay? And I'll write F double colon C to mean that F is in the arrow collection of C. Okay, so arrows have boundaries, which are objects. So now we have boundary maps. So there's the domain, which I'll call the negative boundary and write it like this, and the codomain, which I'll also call the positive boundary and write like this. And now arrows are classified by their boundaries into collections. Okay, so sorry, I'm gonna like wrap up to here now. So for the collection of arrows in a category whose domain is an object A and whose codomain is an object B, we will call this collection like this. So this is notation I'm introducing. And we call this the HOM collection. HOM is an abbreviation for the word homomorphism, which means something like arrow. By the way, these arrows are also called morphisms, if you want to be formal about that. Okay? And here, if the category in question is already obvious from the context, we can just write A arrow B and drop the C. Okay? So the arrows are classified by their boundaries. And now we have two ways to make arrows. We have identity arrows. So this means we have a map called id, or I will call it id anyway. And the identity arrow on an object A is in the HOM from A to A. So in other words, both the domain and the codomain object of the identity arrow are that underlying object. So whenever we have a situation like this, where the domain and codomain of an arrow are the same, I will call this informally a loop. And formally, this is an endomorphism, but I won't write that because it takes too long. Okay, well, just this once. Okay, so, so we have identity arrows for every object. And then the final piece of data is we have composition of arrows. So composition is a partial operation on arrows. Which is defined when I have two arrows for and. So if I have two arrows where the codomain of the first is the domain of the second, then their composition is defined. In fact, we call this situation composable. We call these arrows composable. And when two arrows are composable, their composition is defined. By the way, the composition I write with this infix dot. Oops. So in other words, then F composed with G is an arrow from A to C. So it's an arrow from the domain of the first arrow to the codomain of the second arrow. Okay. So that's the data. And then we have some relations. Data satisfying. Some relations called the composition laws. Okay? And this says that if we have an arrow, then if I compose the identity arrow on its domain with the arrow itself, then I just get the arrow itself. Okay? And furthermore, that's the same as if I compose the arrow with the identity arrow on its codomain. So in other words, this is called the unit laws. And the fancy way to say this is that identity arrows are units of composition. That is, when you do a composition with an identity arrow, you just get back the other arrow in the composition. Okay? And then the other law is that if I have 3 arrows, such that the codomain of the first is the domain of the second, and the codomain of the second is the domain of the third, then there's 2 possible ways I can compose them, right? I can take F and compose it with G, that it's composed the first 2, and take the result and compose it with the third one. Or I can compose the first one with the result of composing the second one and the third one. And this says that those are equal. So this is going back to the Lego analogy, right? If I take 3 Lego bricks and I stick the first 2 together and stick on the third one, then it's the same as if I had stuck the second and third one together and put the first one before it. And so this is called associativity. Okay? And whenever we have a situation like this, where we have any number of arrows where the codomain of one is the domain of the next, I will call this a path. A path in the arrows, which means you can stick them together, that they're serially composable. Okay. Maybe this would be a good time to pause and tell you that you don't have to write down everything I say, because there are lecture notes for this course. So if you go to my webpage, which you can find by going to the summer school's webpage, there's a link to it. At the top of the notes section, there's collected notes for this course, where everything is written out with also a lot more detail than I'm able to fit into the time allotted. So, try to absorb what you can from the meaning from the talks, and then if you want to go back and look things up, you can do it offline. Just be careful, there are also notes from a course I gave last year here, so make sure you get the 2016 edition. Okay, so that's what a category is. Let me just make a couple remarks. So the first one is, okay, so ultimately we're going to be talking about equations between arrows, right? Those are the only kinds of relations that we have. And in order for 2 arrows to be equal, they have to have the same domain and the same codomain, right? Otherwise, it's not even reasonable to ask the question, are they equal? Okay, so if the domain of 2 arrows is the same, then we say that those arrows are parallel. I think I might have just said the wrong thing. If the boundaries of the 2 arrows are the same, the domain and the codomain, right, then those arrows are parallel. Parallel means same boundary. Okay. Let's see. Another thing to say about composition is that in many places you will see the composition that I've been writing like this, written like this. Okay? This means the same thing. Both of them just say do F first, then do G. So you could think of this as like G then F if you want to put words to this. And to think of this as G after, wait, did I say the wrong thing? F then G, sorry, or G after F, mean the same thing. Okay, and this is useful when the arrows are actually some kind of real functions, because then you can write that G after f of x is G of f of x, right? Because that's the way we write function application with the argument on the right. So this kind of makes sense when we're working with points, and this kind of makes more sense when we're working in a point-free style. Okay. Last thing I want to tell you on this topic is there's another way to present categories which somehow is closer to the heart of the meaning of what the idea is. And that is, instead of having this binary composition operation here, arrow composition, right? We have a sort of a length indexed composition operation where for any, where did I write the path, for any path of arrows, right? As long as they're serially composable, which is part of the definition of a path, then they have a composite. So this is called an unbiased presentation. And instead of distinguishing the zero-ary composition, which is like an identity arrow, and the binary composition of arrows, we say, okay, for any path, they have a unique composite. And that's sort of the idea that you should take away from the definition. Because if you haven't seen the definition before, it might seem kind of long and not so perspicuous. But the idea is the Lego thing. If you can put the arrows together, then they have a composite. And an identity is just a nullary composite. It's when you have nothing that you're sticking together. Okay, so another way to think about this is there's a graphical language that lets us draw pictures to represent configurations of arrows in categories. And these are called diagrams. And a diagram is just a directed graph whose vertices are labeled by objects in a category and whose edges are labeled by arrows in that category. So for example, if I had objects A, B, and C, and arrows F and G, then I could draw this diagram, right? Assuming that they were composable in this obvious way. And because these are composable, they have a composite, F followed by G. And whenever I'm asserting that some morphism exists, I'll use this convention of using a dotted line to just draw attention to this is what I'm talking about. This is what I'm asserting exists, right? So if it's the case that in the diagram there's multiple paths in the edges between two vertices, and furthermore, that the arrows representing the composites of those edges are the same, then we say that the diagram commutes. Okay? So a commuting diagram is one where whenever there's a pair of paths between the same boundary, so between the same start node and end node, if the arrows represented by the composites of those edges in the diagram are the same, then that diagram commutes. Does that make sense? Well, this is one, right? So F followed by G is a arrow in the category, and namely it's exactly this one, the one called the composite of F and G. But I'll be drawing more in just a second. Okay, so we can use this language to reason about arrows in a nice way. So first of all, if we have a diagram that commutes, say this simple one, okay, I just have two arrows that are the same, I'm asserting. Then if I take another arrow and compose it with them like this, then that diagram still commutes. So the point is if I stick an arrow onto a commuting diagram, I get a commuting diagram. This is witnessing the fact that equality of morphisms is a congruence for the operation of composition. So this is relating back to something that Dan talked about earlier, right? It's saying that these two things are equal, so therefore if I compose something with each of them, then they remain so. And likewise, if I compose something here, then they remain so too, right? So whenever I have a commuting diagram, I can stick on all the arrows I want, and it continues to commute. And this thing is called, it has the cute name, whiskering. And I think the idea is if you think of this as some kind of little cat, then these are like the whiskers. Okay? And another property of equality of arrows that we can witness by diagrammatic reasoning is that if I have two diagrams that commute and they have a common path, so there's a path that exists in both of the diagrams, then I can stick those two diagrams together along that path, and the resulting diagram will still commute. So let me explain that. Remember, the unit law of composition says that if I have the identity on A followed by arrow F, then that's just equal to F, right? So that's what we call the left unit law. It's saying that the identity is a left unit for composition. Now, ignore this diagram for a second and look at this diagram. This is just the right unit law for composition. It's saying if I have an arrow and I follow it by the identity, it's just that arrow. So now these two diagrams share this edge here. I mean, they also share other edges, but for right now they share this edge. So we can mash them together along that edge, and the diagram still commutes. So that says that if we do the identity followed by F, it's the same thing as doing F followed by the identity, which is probably not surprising, but it's something you can infer just by this graphical reasoning. Okay, so this is the two unit laws of composition. Let's do the associative law. So if you remember that one, we had arrows F and G, and then here we had the composite. Okay, so now let's say we also have an object D, and we whisker this thing by H. So now we have a diagram involving F, G, and H, which says if you do F and G followed by H, then, well, okay, it's the zigzag, but whatever. Now, ignore this part of the diagram for the moment, and let's make the triangle that witnesses commuting here. So here we said if we do G, then H, then we get their composite, which is obvious. Now if we whisker that by F, then we get this diagram. And now this FGH path is common to both diagrams, so we can stick them together along that path. And it's just saying that, well, what we said there, right? If you do F and G followed by H, it's the same as doing F followed by G and H. And so this idea of reasoning graphically is called pasting. And it's just what I said. It's sticking diagrams together along a common path. Okay? Any questions so far? So pasting is the construction of taking diagrams that you may have, finding a path in each of them, which is the same, and gluing them together along that common path. So it's like taking this diagram, identifying this path, taking this diagram, identifying this path, sticking some crazy glue in between, and smushing them together. Okay, so now we've got the definition. Let's meet some categories. So, yeah. Yep. Oh, I should do this thing. Great. In case you want to refer to that. Okay, so let's build a little menagerie of very simple categories. That's the next project. Okay, so let's think about the simplest category we could possibly construct. Okay, I'll draw the diagram for it. So first I have to draw the objects, and then I have to draw the arrows, and then I have to make sure everything commutes, and blah, 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 and I'm done. Because, right, the definition says that for every object there's an identity arrow, but it doesn't say that there's any objects at all. So that's fine. If I have no objects, I still have a category. So this is called, unsurprisingly, the empty category. Whose diagram is here, right? And I'll write that with this Blackboard bold 0 to refer to it. Okay, actually I'll take up less space for its diagram, so I don't have to erase as much, but you know. Okay, let's be slightly less trivial. So let's add an object. Okay, there's an object. I'll call it star. Okay, as soon as I've added the object, I have to add the identity morphism for this object, right? So now I have id star. That has to live there. Now, do I have to add anything else? Well, id star is an endomorphism. It's a loop on star, so it's composable with itself. So I have to say what the answer is when I ask, what do I get when I compose it with itself? But there's only one possible answer because there's only one arrow in the whole HOM, right? So it better be the case that id composed with id is id, but it is, right? Because, perfect, just there, right? It's for this reason twice, because you can substitute f for either the one in the left unit or in the right unit. Okay, so that's good. So this is called a singleton category. And I will use this Blackboard bold 1 to refer to that. Okay, so, but there's no reason to stop at one object, right? We can add more objects. And in this case, if we have a set, we can build a category out of that set where the objects are just the elements of the set, and then the arrows, well, S1 is the set of identities on X, where X is in the set. So it's saying for every element of the set, there's an object in the category, and then for every object in the set, there's a loop, an identity morphism on that object, but that's all. So that's like saying, okay, I have not just one object, but a bunch of objects. And for each one, there's a little loop, namely the identity loop, and that's all. There's no other arrows going between the different objects, and there's no other endomorphisms in each one. So these things are called, oops, I guess I should have put this here. These things are called discrete categories. And they just correspond to sets. Well, okay, modulo issues of cardinality if you care about that sort of thing, right? But for every set, there's a discrete category, which is just the category whose objects are the members of the sets, and the only arrows in sites are the required ones, the identity endomorphisms. Okay. Continuing, let's build something that's not discrete. So I'll remind you a preordered set is a set with a reflexive and transitive binary relation on it, which is generically written as this less than or equal to, right? So we can build a category out of this where the objects well, again, they're just the elements of the set. Okay, but this time we have some arrows that are not identity loops. So I'll tell you what the elements of the HOM from X to Y are for two objects. So if X is less than or equal to Y, according to the preorder, then it's the singleton set consisting of the token called X is less than or equal to Y. Okay, so there's just a token in there witnessing the inequation. And otherwise, it's empty. Okay, so I have to tell you what the identities and the compositions are. Oops, identities. Well, id on an object X is just the token, x is less than or equal to x. And we know that that's true because the preorder relation is reflexive and transitive. In particular, it's reflexive, so that there is something in that HOM. And then the composition says that if we have the token x is less than or equal to y, and we want to compose that with the token y is less than or equal to z, then that's just the token x is less than or equal to z. Right? And again, because the relation is transitive, then we know that that's sound. Okay, so I'll point out a couple things about preorder categories. First of all, each HOM collection consists of either one element or nothing, right? So they're sub-singletons is a fancy way to say that. So, well, as a consequence of this, the laws, they're still there. The laws are trivially satisfied, right? Because if you have an empty set, all elements in that set are equal to each other. Pick any two, right? Pick any two elements of the empty set. I can guarantee that they're going to be equal. Same thing with a singleton set. If you have a singleton set, if you pick any two elements, they're going to be equal. So that's all fine. And in addition, every diagram in a preorder category, or as a consequence, I should say, every diagram in a preorder category has to commute, because there's only one element in any HOM. So if you want to know whether any two parallel arrows are equal, the answer is always yes. You don't have to do any work to check. Okay, so let's think about the simplest preorder category that's not discrete, right? Because this is the project that we're doing in this portion of the talk, is we're building up simple categories. Okay, so we start with one object. Oh, by the way, I'm using this convention. I did it here already, but I forgot to mention it. If I just want to have an object in a diagram and I don't want to bother naming it, I want sort of an anonymous object, I'll just use this dot. And a dot just means some object whose name I don't care about. But in particular, it doesn't mean that if I have two dots in the diagram that they're the same. It just means they're both objects, right? So this is like an underscore in a programming language. Okay, so if there's only one object and all the HOMs are singletons, then it's going to be discrete, right? So we have to add another object. And now if the only morphisms here are the identity loops, then again it's going to be discrete. So we have to add an arrow like this, say. Okay, and now we no longer have a discrete category. We do have a preorder category because all the HOMs are either empty or singletons. By the way, there are little loops here, but from now on I'm not going to draw the loops because you know that they're always there, the identities. Okay, so this is a category called the interval category. And I'll write that with this blackboard bold capital I, which I know looks like the Roman numeral 2, I'm sorry. And again, or not again, I guess I should say. So these categories that we've seen so far, structurally, they're very simple, right? They're like almost too simple to be worth considering. This one has nothing in it. This thing has only one thing in it. This is just a preordered set. This is like, a walking arrow, basically. So although these have very simple structures, they end up having very important properties. So in a subsequent lecture, we're going to see about that. But I just want to mention that by way of foreshadowing. Okay, so I'll do one more of these structured sets as category examples, which is something maybe closer to something that comes up in PL theory. Right, sorry, I guess I should have said, since I'm naming these things, this is a preorder category. So that was discrete, that was preorder, that was empty. Okay. So if we have a monoid, and let me remind you what that is. So a monoid is a set with an an associative binary operation, which I'll write as this like asterisk, but I'll always say is multiplication, right? So it doesn't mean it's the multiplication on the natural numbers or anything. It's just a generic binary operation, which is associative, and I'll call it multiplication. And then it has an object, which is a unit for this operation. So that's a monoid. The category which I'll again use the Blackboard bold thing convention. So this is going to have objects with objects. Well, there's just one. The object collection of the monoid category is a singleton set of one object. So I'll call it star. The arrows, well, there's just one HOM, right? So the HOM in M between star and star is defined to be the set M, the underlying set of the monoid. Okay, and then we have the identities. Well, again, we don't really have identities. We just have one identity, right? Because there's one object. Id on star is defined to be the unit of the monoid. And for composition, if you want to know what x composed with y is in the category, then I just say, well, go ask the monoid. You say, what is x multiplied by y in the monoid? Okay. This is an associative binary operation, so it gives us an associative composition on the endomorphisms. And furthermore, this is the unit for this operation, so this is the unit for this composition. So we get a category of loops. So the way I think about this is like, if I wanted to draw the diagram, I have star, which is the object, and then I have here some arrows, one for each object in the monoid. Right? And if you want to compose these arrows, you just ask the monoid, hey monoid, what's the multiplication? Monoid answers. You say, okay, that's the composition. So when I was a kid, I had this toy called a koosh ball that was made of like loops of rubber bands. That's sort of how I imagine these categories. Okay, so if we want to make a simple, oh, this is called a monoid category. If we want to make a simple monoid category that's not discrete, let's think about how that will go. Okay, well, we have the anonymous object. In order to not be discrete, we need at least one arrow in addition to the required identity, right? So let's add a loop and call it S. But now S is an endomorphism. So in particular, it's composable with itself. So we have to know what S composed with S, and S composed with S composed with S, and so on all are, right? And by the way, I can write this without parentheses because by the associative law, it doesn't matter where I put the parentheses. Okay, well, now we have some choices to make. One choice we can make is to choose not to assign any relations between these composites, just make them all different from one another. And if we do that, then we end up with a monoid which is probably very familiar to you, namely the monoid of natural numbers under addition with its unit, which is 0, right? And the idea is that the natural number just tells you how many times you go around the loop S, right? And addition is just concatenation. If you go around m times and then you go around n times more, then you've gone around m plus n times. And the associativity just tells you that, well, that if you go around, well, yeah, if you go around m times and n times, then p times, it doesn't matter how you associate that. In fact, it's also commutative, but that's not the point here. Okay, so what do I want to say about that? I think that's all I wanted to say about that. Good. So does anyone have questions about that before we move on? Yes?
We haven't mentioned inverses of errors or anything like that.
Nope, not yet. We'll get there. I mean, in particular, though, it's not a part of the definition of a category that there need to be inverses of arrows. There may not be, and in many cases there aren't, right? It's sort of something special about a category that it has inverses for its arrows. So in particular, if you know some abstract algebra, you've seen the monoid category we just constructed. If all the arrows in the monoid had inverses, then what kind of category do you think we would get? A group, exactly. So we would have a group category, but that's for the future. So, right. So where was I going with this? Oh yeah. Okay. So the big picture strategy for today is now I've introduced you to some mathematical constructions that we can consider to be as categories, right? So these are structured sets as categories. So now I want to introduce you to some categories of mathematical constructions, or said another way, some categories of structured sets. Cats of structured sets. Okay, so the simplest kind of structure you can add to a set is no structure at all. Right? So we can just have the category of sets. And I will refer to that using this notation. So when I'm using sort of a proper noun to refer to a category, I'll use this like small cap convention. Doesn't really matter, but okay. And so what are its objects? Well, they're sets. What are its arrows? Well, okay, now it kind of depends, right? It depends what your set theory is, but let's just sort of be parametric on whether what set theoretic axioms you're assuming or whatever. But they're functions, whatever your notion of function may be in your set theory. Okay, and then of course now we have to talk about what are identity arrows, but they're just identity functions that ought to exist no matter what your set theory is. And composition of arrows should be composition of functions, and you should be able to define that, right? So in particular, if I have, this is again a good place to use this notation, right? G after f of x being g of f of x, right? That's the way we compose functions. Okay, and then you should check that the unit and associative laws are satisfied, but of course they are. Right. So the next kind of structured set I want to talk about is, so before we did discrete categories and then sets as instances of that, and now we have the category of sets. Next we talked about preordered sets as categories. So now we can talk about categories of preordered sets. And I guess I'll just say the category of preordered sets. I'll refer to that like this, although I don't think I'll ever refer to it again. So. Okay, so its objects are, well, preordered sets. We saw what those were a few minutes ago. And what are its arrows? So what's the right notion of function between preordered sets? Exactly. It's what's called a monotone map. And in particular, those are functions which preserve the order. So if x is less than or equal to y in the domain, then f of x is less than or equal to f of y in the codomain. Okay? And now, I already gave you as an exercise to check that the associative and unit laws are true of functions. So they're automatically true of order-preserving functions. But now you need to check that, that the identity function is monotone and the composition of monotone functions is monotone, right, in order to conclude that this is a category. So I'll let you do that offline if you want. Okay, and then recapitulating our story here, the last category we had to consider is the category of monoids. I'll call this mon. OK, so this is probably starting to look familiar. The objects are monoids, which we introduced a few minutes ago. The arrows are what are called monoid homomorphisms. And what those are is structure-preserving maps of monoids. So in particular, i.e., there. Oh, OK. So then a monoid morphism f from the monoid m star epsilon to the monoid, say, n star prime epsilon prime. Right. So I'm defining what this morphism in this category is. It's just a function, so that is a morphism in the category of sets between m and n, such that, well, if f of, what do we call this, x star y is equal to f of x, now star prime, f of y, right? So it preserves the multiplication, and furthermore, it preserves the unit. Okay? So they're just structure-preserving maps of monoids. And then I'll leave it as an exercise to check that they satisfy the laws of the category. Okay, so we could continue like this, but we won't because it would be boring. But abstract algebra gives us a lot of categories like this. So categories of groups, categories of rings, categories of modules over rings, categories of vector spaces, and you can go on and on. But for our purposes, maybe a more interesting category has to do with the types and terms of a programming language. Okay, so I can only give you the beginnings of this story today. We'll have to hold it into abeyance and come back to it later. But the idea is that the objects are interpretations of, whatever that means, types. Okay, so these brackets are meant to represent interpretation, and this is some type, or more generally, of typing contexts. And then arrows are interpretations of terms in context. So if I have a term m of type A in context gamma, like that, then its interpretation should be some arrow between the interpretation of the context and that of its type. Right? So the point is that, I think Bob mentioned this earlier in his talk, right? You think of the terms as some kind of morphisms, where the domain of the morphism is the context of variables that it contains, and the codomain is its type. And when we already know what the gamma and the A are, we can just write M as a shorthand here. Right? Because we can recover this and this by looking here. Okay, so, so we can't go very far with this yet because we need a way to build interpretations of contexts and of non-atomic types, but question?
So this means that the objects in our category are sort of bifurcated into two types of objects?
No, it doesn't. Okay. The answer to why I won't really be able to explain until later, but the short answer is you can always think of a type as like a singleton context, right? Context with one thing in it. Namely, if I have x colon A as my gamma, then that's somehow the same as just A.
Okay. But I'm not going to have very many
Sorry?
How would I get arrows that I can compose? To go into a singleton.
It just means that there's, so as Dan said in his lecture this morning, right, the simplest kind of context you can consider is a context with one variable, a one variable context. But you can still compose things. I'll get there in just a second, okay? So the simplifying assumption that we're making here is that A, all the types are atomic, and B, all the contexts are singletons. That doesn't mean there's only one type in the system. It just means that every term has a single variable free in its context. Okay, so this is we're gonna describe a baby type theory. With these simplifying assumptions. Okay, and now the idea is, since we're trying to interpret these things as arrows as in categories, right? We want the terms to be arrows in categories. We want to talk about what the identity arrows are and what the composition of arrows are. Okay, so if I have this term in context, right? I think Bob referred to this as the variable rule or something like that, which should be admissible in any sane structural type theory. Then its interpretation should be the identity on the interpretation of the type A, right? Which makes sense because the interpretation of the context is this, right? And then the interpretation of the type is this. They're the same, so we get an endomorphism, so it makes sense for the identity to be in that HOM. Okay, and then for composition, if we have this term in context, so this is my notation for substitution. It's just the term n with the only variable in n substituted for the term m. Then we want this to be equal to, well, okay, so this interpretation to be equal to the composition of this with, I'll write it vertically because I'm running out of room. And I realize I forgot to give a type to this one, so sorry for the squeezing. But the point is, right, if m is a term of type B in a context A, I won't bother naming the variable because there's only one in our baby type theory, and n is a term of type C in a context B, then if I interpret these as arrows from A to B and from B to C respectively, and I compose them, then I get an arrow from A to C. Now if I look at this term, right, n had a B free in it, but m gives you a B as long as you give it an A. So if you substitute the m for the free variable, wait, something's wrong here. If I substitute m for the free variable in n, then I get something that gives you a C as long as you give it an A. So the boundaries work out right. Does it make sense? Okay, so that's, oh wait, actually that's not quite it. I'm going to slightly more for this part of the story. So we can't go too far with this story yet, but I will point out one thing. And that is that there's a couple ways we can do substitution when one of the terms involved is a variable, right? So if I have this term in context, if I just substitute x for itself, right, then what do I, oh, and then I need to give this a type. Then what is this? What do I get if I substitute x for itself in m? Just m, right? Okay, so let's do the interpretation we proposed here. And then this says that this should be equal to, well, what do? I compose the interpretation of this term in context with the interpretation of this term in context. Okay, but what's the interpretation of this term in context? This is the identity on A, right? Wait, sorry. It's in the wrong place. That's the identity on the interpretation of A. And then the unit law tells us, right, that this composition is just this thing, which agrees with what we said substitution tells us in the type theory. Do you see that? Okay, and then similarly, we can do this one. And I won't go through it here, but you should look and see that if you interpret this, then by the other unit law of composition, that what substitution tells you agrees with what our proposed semantics tells you. And then finally, if you have three terms and that you can you can substitute in two ways. I won't go through that here, it's in the notes, but you can see that that is exactly the associative law of composition in categories. So for this restricted kind of baby type theory, it turns out that this proposed semantics is sound with respect to the way substitution works in the type theory. Okay. Right? So let me change gears here. Okay, so before we took the little detour about type theory, we had built categories of structured sets. No, sorry, the other way around. First we had structured sets interpreted as categories, and then we built categories of those structured sets, right? So if you think about that, that means that the latter were categories of categories, right? Because the objects in them could be interpreted as categories. Okay, so let's think about this idea of categories of categories. Okay, well, in each case, an object was some kind of structured collection, and an arrow was some kind of structure-preserving map between them, right? Just like the preorder monotone functions and the monoid homomorphisms. So, while categories themselves are some kind of structured collections, right? So we should ask ourselves, well, what should be the idea of a morphism of categories? Okay, and the answer to this is the concept of a functor. So for categories C and D, we have an object map. Oh, okay, so, functor f from C to D is, first we have an object map, f sub 0. So just like with the categories, we said what were its objects and what were its arrows. Now we have to say how a functor acts on objects and how it acts on arrows. Okay, so this goes from the object collection of C to the object collection of D. And then we have an arrow map from the arrow collection of C to the arrow collection of D. But now it has to have some properties. So let me continue over here, such that. So it has to have two properties. One, it respects the boundaries, like a good office mate, right? And that means that if F is an arrow in C between A and B, then it takes that to f of f, which is now an arrow in D, whose domain is f of A, and whose codomain is f of B. Right? Oh, sorry, so I just did something which I didn't explain. So typically, as soon as I've introduced these subscripts on the functor, I will drop them because you can always tell, right, if I'm applying this to, say, an object, then I mean f0. And if I'm applying this to an arrow, then I mean f1. So we can just drop the subscripts because we can always recover them as needed. Right? So it just means, to say this another way, the domain of the functor image is the image of the domain, and likewise with the codomain. Make sense? Okay, and then it also has to respect the composition structure. By which I mean, if I have in C an identity arrow, so I'm going to start using my diagrammatic notation. So this is an identity arrow in C. It gets mapped by the functor f to an identity arrow in D. Okay, and what are the boundaries here? Well, they're what they have to be because of this, right? And so, okay, it respects identities, but then it also respects composition. So if we have here a composite in C, okay, so here is F and G, two arrows in C, and they have, therefore, a composite, F then G. Then this gets mapped to, well, okay, this arrow gets mapped to F of F, and this one gets mapped to F of G, and this one gets mapped to F of the composition F followed by G, right? And so this is saying that this triangle commutes in that the composition of the images is the image of the composite. Does that make sense? Okay, so it may sound kind of technical, but I want to maybe pause for a moment and try to reassure you that it's like what it ought to be, right? It's like if you want to invent this, this is probably what you come up with because it's the most reasonable thing, right? It has to send the object somewhere. It has to send the arrows somewhere. It should send them to places where they fit together, right? Otherwise, it would be like, taking them and jumbling them up and throwing them on the floor and they don't fit together anymore. And furthermore, if you have some kind of diagram in C, you should be able to take the whole diagram and shift it over by the functor and it remain a diagram. In particular, if it's a commuting diagram, then it should remain a commuting diagram. Okay? So, I don't know. If this is not intuitive, then hopefully I want to convince you that it's exactly what it ought to be. Okay. So, now we have an idea of morphisms of categories, or a candidate idea for morphisms of categories. But in categories, we always have identity morphisms and morphism composition, right? So that means that if we want to make categories of categories in general, we have to say what identity functors are and what functor composition is. Okay? But then they're just, again, exactly what they ought to be. So the identity functors well, if I have a diagram in the domain category, if I just have, oops, that's not, wait, what do I want to do? No, okay. Well, okay, if I have just an arrow in the domain category, then it takes it to that same arrow in that same category. Right? Because it's an identity functor. So remember, an identity morphism has the domain is the same as the codomain, so it has to be an endomorphism of the category C. It has to take objects to objects and arrows to arrows in such a way that they fit together. But I'm just saying, look, it just takes objects to themselves, and it takes arrows to themselves. It does nothing, right? It's just what you would expect. And then if we have a functor composition, and so here, if I have an arrow in C, and it's taken to an arrow in D by the functor f, so this is f of f. And then if I have a further functor, say G, that goes from the category D to the category E, then this takes the arrow to G of f of f, right? And I didn't bother labeling the boundaries because they are what they have to be by boundary respecting this. Okay? So now we have a notion of morphism of categories, namely a functor. We have identity such. We have compositions of such. Okay? It's pretty obvious, but you should just check that this is a unit of composition and that this kind of composition is associative. So now we can have categories of categories. Okay? So it's a fact that if you have some collection of categories, some collection of functors between them, and some collection of functors between them, you can make a category whose objects are the categories, whose arrows are paths in the functors, right? Whose identity arrow is the identity whose identity arrows are the identity functors, respectively, and whose arrow composition is functor composition. Does it make sense? Okay, so we can have categories of categories, but we have to be careful because we can't have the category of all categories for the same reason that we can't have the set of all sets, right? Whenever we start to get foundational, we always have to be a little bit careful. So, so we have to consider matters of size. Okay, so this part, if you know a bit of set theory, what I'm about to say is going to probably make sense, and you'll just shake your head and say, oh yeah, of course. If you don't know any set theory, then don't worry too much about this, right? Well, okay, it's kind of its own thing. So a collection, so if I've been careful up until now, I've always referred to HOMs as collections and as the objects of a category as collections. A collection is called small if it's a set. Well, a small collection is a set, okay? And okay, you can ask me, what do I mean by set? And really, it doesn't matter. Again, it's kind of parametric on your set theory. We say a category is small if its collection of arrows is small. And if you think for a moment, you say, what about the collection of objects? Well, remember, for every object, there's an identity arrow on that object, so that there's at least as many arrows as there are objects in any category. So if the collection of arrows is small, then the collection of objects must also be small. Okay? So, right. Okay, so we have a category of small categories. And I'll call that cat, like this. Okay, so it has objects, small categories, and arrows, the functors between them. But in particular, it's not the case. So cat is not an object of cat. Okay, for the same, well, okay, for the same foundational reasons that you can't have the set of all sets. Okay. Right. Okay. What else do I want to say about this? Oh, yeah. Okay, so many times we don't care if a category is small sort of globally, but we only care whether each of its HOM collections is small. So a locally small category has small HOMs. Okay, and in particular, the category of sets and the category of small categories are both locally small, and all the categories that we'll be talking about in this course are locally small. So from now on, I will just say Hom set rather than Hom collection, and assume that everything we're talking about is locally small. Okay, let's see. Try to do that. I still have a few more minutes? Yeah? Okay. So I'll do one more topic here. Okay, so because we're dealing with locally small categories everywhere, and therefore the Hom collections are sets, that puts the category of sets in sort of a distinguished position. So let me try to explain what I mean by that. Let's fix an object in a category. Okay, then we can define a function, which I will call C x arrow blank, right? And this is a function from that sends an object in C to the set of arrows in C from X to A. Okay? So it sends a C object to a set. It sends a C object to a set, namely the set of arrows from the distinguished object to the object that we just fed it. Okay? Now, we can extend this, so this is a function. We can extend this function to a functor. Okay? But in order to do that, we have to say if I have an arrow, what does this map do to that arrow? Okay? And what it does is, well, we write it like this. But this is just syntactic sugar. This doesn't mean anything. So I'm going to tell you what it has to be in a second. But let's figure out what its boundaries have to be first of all. Right? So this has to be some kind of map from the image of the domain. So that's this, to the image of the codomain, which is this. Right? So remember, this is the set of arrows from X to A, and this is the set of arrows from X to B. And what I've given it is an arrow from A to B. And remember, we're ending up in the category of sets where the morphisms are functions, right? So putting all this together, what we want is a function that can use this arrow F to turn an arrow from X to A into an arrow from X to B. So any thoughts of how we could do that? We have an arrow from A to B. We just compose them, right? So this is defined to be blank compose F, okay, which of course is syntactic sugar for like, this is like lambda A dot A compose F or something like that, right? It just says take the argument and compose it with F. Okay, so we can define this function and extend it to a functor. Right? This part up to here was the function map. It told us what to do with objects. But to make it a functor, we had to say what to do with arrows too. Okay, so such a functor, sorry, is called a representable functor. So this is called a representable functor. Okay, and X is known as the representing object or the representative of the functor. Okay, so let me be clear what I've what I'm asserting and what I've proved, right? I've defined a function. I've extended it to be defined on maps. But in order to prove that it's a functor, I have to show, what do I have to show? Is it still up there? No, it's not still up there. I have to show that it respects boundaries, but okay, it does. We just saw that. And then I have to show, what does it respect? The composition structure, remember? Which means that it sends identities to identities and composites to composites. So let's see if that's the case. Okay, so we want to show two things. That C, X, arrow, in A is equal to the identity function on C, X, arrow, A, right? So this is this functor applied to the identity on A arrow. And this is the identity function on this set. Okay, so, and likewise, we need to show that C, X, arrow, F compose G is equal to like this. Right? Because now this is the representable functor applied to this argument here, right? And to preserve composition, it says that the functor applied to the composition is the composite, in this case of functions, because we're landing in sets, of the respective things. Okay, so the proof of this is in the notes. I'm not going to go through it at the board because I don't want to take the time, which I'm almost out of apparently. Yeah, so let me see. What else do I want to say? I guess, is that it? Am I out of time? Or, this seems like a good place to stop. Well, at least take questions if anyone has any. Yeah?
Is the intuition of the reader modes right here for representable functors?
Sorry?
Is the intuition of the reader monads a right intuition for representable functors?
Of what kind of monads?
Reader monads.
Oh, reader monads.
Yeah.
Okay, well, let's talk about that offline, okay? Because I haven't talked about monads or anything at all yet, so. Okay. I mean, I think someone asked earlier, like, is something an implication of the Yoneda lemma? And the answer is almost certainly yes, but like, but why that's the case is a longer discussion, right? Okay. Anything else? Okay.